Welcome to today's problem walkthrough. We'll be tackling problem number 1423, titled Maximum Points You Can Obtain from Cards. In this problem, we'll explore how to maximize the points you can collect while making strategic choices. Let's dive in and break it down step by step. In this problem, you are given an integer array called card points, where each element represents the points you can earn by selecting that specific card. Additionally, you're provided with an integer k, which represents the exact number of cards you need to pick. The selection process allows you to pick cards either from the beginning or the end of the array, one card at a time. Your goal is to determine the maximum possible score you can achieve by selecting exactly k cards. The input consists of the array card points and the integer k, with constraints that the length of the array can be as large as 100,000, and the values within the array can go up to 10,000. The output will be a single integer representing the maximum score achievable under these rules. Let's explore some examples to better understand how this problem works. For the first example, the input array card points is 1, 2, 3, 4, 5, 6, 1, and k is 3. The task is to select exactly 3 cards to maximize the score. In this case, the optimal solution is to pick the last card, which is 1, the second to last card, which is 6, and the third to last card, which is 5. Adding these values gives a total of 12 points, which is the maximum score you can achieve. The output for this example is therefore 12. This demonstrates the importance of carefully choosing cards from either end of the array to maximize the total score. Now, let's look at another example to see how the approach works in different scenarios. In the second example, the input array is 2, 2, 2, and k is 2. Here, you need to select 2 cards to maximize the score. The optimal choice is to pick the first 2 cards, which gives a total score of 2 plus 2, resulting in 4. This is the highest score possible given the constraints, so the output is 4. In another scenario, if the size of the array equals k, such as in the third example with card points equals 9, 7, 7, 9, 7, 7, 9, and k equals 7, you must take all the cards. The sum of all elements in the array, which is 55, becomes the result. This case highlights that when k matches the size of the array, no selection is needed, the total sum is the output. Understanding the constraints and edge cases is crucial for solving this problem efficiently. First, if k equals the size of the array, the result is simply the sum of all elements in card points. Second, if k is 1, the solution involves selecting the maximum of the first or last card. However, for larger inputs where the array size can reach up to 100,000, an efficient solution is necessary. Instead of directly calculating the sum of all possible k selections, which would be computationally expensive, we can approach the problem by focusing on the cards not selected. Specifically, by minimizing the sum of the unselected subarray of size len, card points, k, we can indirectly maximize the sum of the selected k cards. Using a sliding window technique, we can compute this efficiently in O(n) time, ensuring that the solution scales well for large inputs. To solve this problem, we first considered the brute force approach. The intuition here is straightforward. Since we're allowed to take cards from either the beginning or the end of the array, we can simulate all possible ways of picking k cards. For each combination, we calculate the total points and keep track of the maximum sum we encounter. Implementing this involves using 2 nested loops, one to iterate through the number of cards taken from the start and the other to account for the cards taken from the end. For example, if we take I cards from the beginning, we calculate the sum of ki cards from the end, repeating this for all values of I between 0 and k. However, this approach has significant drawbacks. While the space usage is efficient, requiring no additional data structures, the time complexity is k squared. This quadratic complexity arises because each split of k cards requires a new sum calculation, making the approach inefficient for larger values of k. Additionally, many of these calculations are redundant, which suggests there's room for optimization. A more efficient alternative is the optimized sliding window approach. The intuition here is to reverse our perspective. Instead of focusing on directly maximizing the points from k cards, we aim to minimize the sum of the nk cards that we leave behind in the middle of the array. The reasoning is simple. Since the total sum of the array is fixed, subtracting the smallest possible sum of the nk cards from the total will yield the maximum sum of the k cards we take. To achieve this, we use a sliding window of size nk to find the subarray with the smallest sum. First, we compute the total sum of the card points array. Then, using the sliding window, we efficiently track the minimum sum of any subarray of size nk. Finally, subtracting this minimum sum from the total gives us the maximum points. This approach is far more efficient, with a linear time complexity of O(n), since we compute the total sum in one pass and slide the window in another. Additionally, it requires no extra space, making it optimal in terms of both time and space. By avoiding redundant calculations, this method is well suited for handling larger inputs. The sliding window approach stands out as the chosen strategy for solving this problem due to several key observations. First, the total sum of the card points array remains constant, which allows us to shift the problem to minimizing the sum of the nk cards rather than directly maximizing the k cards. Second, the relationship between the total sum and the subarray sum simplifies the problem into an elegant mathematical formulation. Finally, sliding windows are an ideal tool for efficiently finding the sum of subarrays of a fixed size, making this approach both practical and computationally efficient. An important realization, or aha moment, is that by reframing the problem to minimize a subarray sum instead of maximizing k cards, we eliminate the need for the redundant calculations inherent in the brute force approach. While the brute force method is conceptually simpler and easier to implement initially, the sliding window approach is far more efficient. Its linear time complexity makes it well suited for large input sizes, and it leverages a deeper understanding of the problem structure for a concise and effective solution. This balance of efficiency and elegance is why the sliding window approach is preferred. Ultimately, the sliding window approach is the clear choice due to its optimal time complexity and practicality for handling large input sizes. While the brute force method may work for smaller cases, its inefficiency makes it unsuitable for real-world scenarios with large arrays. The sliding window approach not only avoids redundant calculations but also provides a streamlined and elegant solution by leveraging the fixed total sum of the array. This efficiency, combined with its simplicity and implementation once understood, makes it the best strategy for solving this problem effectively. By focusing on minimizing the sum of the middle subarray, we achieve our goal of maximizing the points obtained from k cards in a computationally feasible way. This makes the sliding window approach both an intuitive and powerful solution to the problem. To understand this problem, imagine you have an array of integers, card points, where each element represents the points on a card. You are allowed to pick exactly k cards, but the catch is that these cards must be chosen consecutively from either the beginning or the end of the array. The challenge is to maximize the total points you can obtain from these k cards. To tackle this, we can break down the solution into a few steps. First, we need to fully grasp the problem. You can only pick a total of k cards, and these cards must be contiguous, either from the leftmost side of the array or the rightmost side. The goal is to maximize the sum of the selected cards. Now, a brute force approach to solve this would involve enumerating all possible combinations of splitting the k cards between the two ends. For example, you could pick all k cards from the left, all k cards from the right, or split them in different ratios between the two ends. For each combination, you would calculate the sum of the selected cards and track the maximum sum across all combinations. However, this approach involves computing sums for multiple combinations, which can be inefficient. This leads us to an optimized strategy using the sliding window technique. Now, instead of directly enumerating all combinations, we can simplify the problem by reframing it with an important insight. If you think about it, selecting k cards from either end is equivalent to removing nk cards from the array, where n is the total number of cards. By minimizing the sum of the nk cards that are excluded, we maximize the sum of the remaining k cards. This insight allows us to use a sliding window approach to efficiently find the smallest sum of a subarray of size nk. The steps for this approach are as follows. First, calculate the total sum of all the cards in the array, which we'll call total sum. Then, use a sliding window to find the smallest subarray sum of size nk. Start by initializing the window sum with the sum of the first nk elements. As the window slides to the right, dynamically update the window sum by adding the new incoming element and subtracting the outgoing element. During this process, keep track of the minimum window sum encountered. Finally, subtract the smallest subarray sum from total sum to get the maximum possible points from the chosen k cards. For edge cases, note that if k equals n, the result is simply the total sum of the array since all cards are chosen. If k is 0, the result is 0 because no cards are selected. And if nk equals 0, the window size covers the entire array, meaning the result is the total sum minus 0. This sliding window approach is particularly efficient because it calculates the sum of the nk subarray dynamically, eliminating redundant computations. Instead of recalculating the sum for each possible subarray, the window adjusts incrementally by adding the new incoming card and removing the outgoing card. By focusing on minimizing the sum of this excluded subarray, we indirectly maximize the sum of the cards we choose. In terms of data structures, we primarily rely on the input array, card points, to hold the card values, and the sliding window technique to dynamically manage the subarray. The sliding window itself is implemented using variables to track the current window sum and the minimum subarray sum. This makes the approach both efficient and simple. As for complexity, the time complexity is O(n), where n is the total number of cards in the array. This is because we make a single pass through the array to calculate the total sum and another pass to find the smallest subarray sum. The space complexity is O(1), as we only use a few variables to track sums, without any additional data structures. The implementation of this algorithm is also straightforward. In the code snippet, we first calculate the total sum of the array and determine the window size, which is nk. Then, we initialize the window sum with the first nk elements and slide the window across the array, updating the sum dynamically and tracking the minimum window sum. Finally, the result is obtained by subtracting the smallest subarray sum from the total sum. Let's walk through an example to see how this works. Suppose the input array card points is 1, 2, 3, 4, 5, 6, 1, and k is 3. First, compute the total sum of the array, which is 22. Next, calculate the window size, nk, which is 7 minus 3 is equal to 4. Initialize the window sum with the first 4 elements, 1 plus 2 plus 3 plus 4 is equal to 10. Now, slide the window to the right. Add the next card, 5, and remove the first card, 1. The window sum becomes 14. Continue sliding by adding the next card, 6, and removing the second card, 2. The window sum becomes 18. Finally, slide again by adding the last card, 1, and removing the third card, 3. The window sum becomes 16. The minimum window sum encountered during this process is 10. Subtract this from the total sum, 22 to 10, to get the maximum points, which is 12. Therefore, the maximum points you can obtain from the chosen k cards is 12. This example demonstrates how the algorithm efficiently computes the result using the sliding window technique. This solution efficiently calculates the maximum points you can obtain from cards by using a sliding window technique. The problem requires selecting k cards either from the beginning or the end of the array. The approach is based on minimizing the sum of the remaining nk cards, which indirectly maximizes the sum of the selected k cards. First, the size of the sliding window is determined as nk. This is the portion of the array we want to minimize, as the remaining part contributes to the maximum score. The sum of the initial window of this size is calculated, and it is taken as the initial min_window_ sum. The sliding window is then moved across the array. For each step, the sum of the current window is updated by adding the new element entering the window and subtracting the element leaving the window. The smallest sum encountered during this process is stored as min_window_sum. Finally, the total sum of all the card points is calculated. Subtracting the min_window_sum from the total gives the maximum points obtainable by selecting k cards. This approach is efficient with a time complexity of O(n), as the sliding window requires only a single pass through the array. Here, we start by defining a method called maxScore that takes in an array of integers called card points and an integer k. The goal is to determine the maximum points we can obtain by picking k cards from either the start or the end of the array. First, we calculate the size of the sliding window, which is equal to the total number of cards minus k. This window represents the portion of the array that we will try to minimize in terms of its sum, because the smaller the sum of this window, the larger the sum of the remaining elements, which are the ones we want to maximize. Next, we initialize the sum of the first window of size window size. Using a simple loop, we iterate through the first window size elements of the array, adding their values to current window sum. At this point, we also set min window sum to the value of current window sum, because this is the smallest window sum we've encountered so far. After that, we slide the window across the array. For each new position of the window, we update the sum by adding the next element in the array and subtracting the element that is leaving the window. We then compare the updated current window sum with min window sum and store the smaller of the two. This ensures that by the end of the loop, min window sum holds the smallest sum of any window of size window size. Finally, we calculate the total sum of all elements in the array by iterating through it and adding each value to total sum. This total sum will be used later to calculate the maximum score. To find the maximum score, we subtract the smallest window sum, which we stored in min window sum, from the total sum. Essentially, this subtraction leaves us with the sum of the elements outside the smallest window, which represents the maximum points we can obtain by picking K cards. Finally, we return this result. The algorithm is efficient because it uses a sliding window technique to calculate the minimum window sum in O(n) time and a simple loop to compute the total sum, also in O(n) time. This approach ensures that the solution is optimal and works well even for large input sizes. To solve this problem, we need to select 3 cards from either the start or the end of the given array to maximize the total points. Instead of calculating the sum for every possible combination, we use the sliding window technique to do this efficiently. First, we determine the length of the array, which is 7, and compute the size of the sliding window as the total length minus k, giving us a window size of 4. Then, we calculate the sum of the first 4 elements in the array, which is 1 plus 2 plus 3 plus 4, resulting in 10. This value becomes our initial current window sum as well as the initial min window sum since we are aiming to find the smallest sum of any sliding window of this size. Now, we slide the window across the array by adding the next element and removing the first element of the previous window, recalculating the sum as we go, and keeping track of the minimum sum encountered. In the first iteration, we add the 5th element, which is 5, and remove the first element, which is 1. This updates the current window sum to 10 plus 5 to 1, which equals 14. The min window sum remains 10 as it is still the smallest sum so far. In the second iteration, we add the 6th element, which is 6, and remove the second element, which is 2. This updates the current window sum to 14 plus 6 to 2, which equals 18. The min window sum again remains 10. Finally, in the third iteration, we add the 7th element, which is 1, and remove the third element, which is 3. This updates the current window sum to 18 plus 1 to 3, which equals 16. The min window sum remains unchanged at 10, as it is still the smallest sum among all the windows. At this point, we calculate the result. The total sum of the array is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 1, which equals 22. To find the maximum score, we subtract the smallest window sum, 10, from the total sum. This gives us 22 to 10, resulting in a maximum score of 12. For the second example, where all 7 cards need to be picked, the task simplifies significantly. Since we are taking all the cards, there is no window to slide, and the result is simply the total sum of the array. In the second example, the total sum of the array is 9 plus 7 plus 7 plus 9 plus 7 plus 7 plus 9, which equals 55. Since the window size is 0, there is no subarray to consider, and the min window sum is effectively 0. The maximum score is therefore the total sum minus the min window sum, which is 55 to 0, resulting in an output of 55. In the third example, with the array 100, 40, 17, 9, 73, 75, and k equals 3, we start by initializing the variables. The length of the array is 6, and the window size is 6 to 3, which equals 3. The sum of the first 3 elements, 100 plus 40 plus 17, is 157, which is both the initial current window sum and min window sum. Next, we slide the window across the array to find the minimum sum of any subarray of size 3. In the first iteration, we add the 4th element, 9, and remove the first element, 100. This updates the current window sum to 157 plus 9 to 100, which equals 66. The min_window_sum is updated to 66 as it is smaller than the previous value. In the second iteration, we add the fifth element, 73, and remove the second element, 40. This updates the current_window_sum to 66 plus 73 to 40, which equals 99. The min_window_sum remains 66. In the third iteration, we add the sixth element, 75, and remove the third element, 17. This updates the current_window_sum to 99 plus 75 to 17, which equals 157. The min_window_sum remains 66. Finally, we calculate the total sum of the array, which is 100 plus 40 plus 17 plus 9 plus 73 plus 75, resulting in 314. The maximum score is the total sum minus the min_window_sum, giving us 314 to 66, which equals 248. Here, we are analyzing the time complexity of the sliding window solution. The process begins with calculating the window size, which is derived as the difference between the length of the array, n, and the number of cards we are allowed to pick, k. This calculation is a simple arithmetic operation and therefore takes constant time, O1. Next, we compute the sum of the first subarray of size window_size. This involves summing up window_size elements, which requires O, window_size, or O, and k, time. Once the initial sum is computed, the window is slid across the array. For each new position of the window, a single addition and subtraction are performed to update the sum, and this operation is repeated, n window_size, times, which simplifies to O, k. Additionally, the total sum of the array is computed once, which involves iterating over all n elements and takes O, n, time. Finally, the computation of the result requires one subtraction, which is an O1 operation. When you combine these steps, the total time required can be expressed as O and k plus O k plus O n. Now, when we simplify the combined time complexities, we observe that n dominates both k and nk. Therefore, the overall time complexity of the algorithm is simplified to O, n. This linear time complexity is highly efficient, as the algorithm processes the entire input array at most a few times regardless of the size of k. Moving on to space complexity, the algorithm is incredibly space efficient. It only uses a constant amount of extra space, as no additional data structures are required. The variables such as window_size, current_window_sum, min_window_sum, and total_sum are all integers, and their space usage is O1. The input array card points is read directly without creating any additional copies, so it does not contribute to extra space either. Hence, the total space complexity of the solution is O1, making it optimal in terms of memory usage. To understand why the sliding window approach is more efficient, let's compare it to the brute force method. The brute force solution involves calculating the sum for every possible combination of k cards taken from either end of the array. For each combination, the total sum is computed and the maximum is recorded. This involves iterating through all possible combinations, leading to a time complexity of O, k*n. By contrast, the sliding window approach reduces this complexity to O, n, by focusing only on minimizing the sum of a single subarray of size nk. Both approaches use O1 space since no additional data structures are needed, but the sliding window method is computationally far superior, especially for large inputs. Additionally, the performance of the sliding window approach is consistent across best, average, and worst cases, as the algorithm always processes the array in linear time. This makes it highly reliable for any input size or configuration. Finally, let's validate the big O complexity mathematically. The algorithm involves three main linear operations. First, we compute the sum of the initial window, which requires iterating through window_size elements. Second, the sliding window operation iterates through the remaining k elements, performing constant time updates at each step. Third, the total sum of the array is calculated once by iterating through all n elements. Since all of these steps are linear, their combined complexity is O, nk, plus O, k, plus O, n. When simplified, this becomes O, n, as n is the dominant term. Therefore, the big O complexity of the algorithm is mathematically valid as O, n, confirming that the solution is both efficient and scalable for large inputs. Understanding common mistakes is essential to avoid pitfalls and excel in solving this problem. One major mistake is not considering edge cases. For instance, scenarios like arrays with fewer than k elements, arrays where all values are equal, or when k is 0 can lead to incorrect calculations or even runtime errors. To address this, always verify the input constraints and explicitly test these edge cases during your development process. Another frequent issue is overlooking the sliding window optimization. Many candidates rely on a brute force approach, repeatedly computing the sum 4k subarrays, which results in an inefficient O(k*n) time complexity. Instead, leveraging the sliding window technique allows you to maintain a running sum and reduce the complexity to O(n), drastically improving performance. Lastly, it's important to carefully interpret the problem. For example, some mistakenly sum the k largest values in the array, ignoring the two-sided picking constraint. This misunderstanding leads to incorrect results. To prevent this, take the time to read the problem description thoroughly and ensure you fully grasp the constraints and requirements before diving into the solution. In addition to those, there are other common errors to watch out for. Off-by-one errors in indexing are particularly troublesome. These occur when you include extra elements or miss boundary cases while summing from the beginning or the end of the array. To avoid these mistakes, double-check all your loop indices and ensure they align with the intended logic of your solution. Inefficient memory usage is another concern. For example, creating multiple copies of the array during computation significantly increases memory consumption. Instead, consider optimizing your approach by modifying indices or using pointers, which allows you to achieve the same result without unnecessary overhead. These adjustments not only improve the efficiency of your code but also demonstrate good programming practices, which interviewers and competitive programming platforms value highly. To succeed during interviews, it's important to focus on key strategies and demonstrate your strengths. One of the most valuable techniques in this problem is identifying sliding window patterns. Problems involving sums or subarrays often benefit from this optimization, and being able to spot it quickly can lead to more efficient solutions. Additionally, make sure to articulate your problem-solving process. Even if you start with a brute force approach, explaining how you plan to optimize it shows interviewers your critical thinking and adaptability. It's also helpful to highlight trade-offs between different approaches. For instance, comparing the time and space complexities of brute force at O(k*n) versus sliding window at O(n) shows a deeper understanding of algorithm design. Lastly, practice is key. Familiarity with similar problems, such as those involving sliding windows, prefix sums, or dynamic programming, will help you recognize patterns and apply relevant techniques more effectively. Some excellent related problems to review include LeetCode 209 for minimum size subarray sum, LeetCode 904 for fruit into baskets, and LeetCode 1004 for max consecutive ones 3. Each of these problems reinforces the concepts and strategies discussed here, making you better prepared for variations you might encounter. Finally, let's explore some alternative approaches that can be useful depending on the scenario. The prefix sum approach involves pre-computing prefix sums for the array, which allows you to calculate the sum of any subarray in constant time. By comparing all combinations of k cards from the beginning and end, you can determine the maximum points. However, this comes with the trade-off of increased space complexity to O(n) due to the prefix sum array, although the computation itself remains efficient at O(n). Another option is the two-pointer approach. Here, you calculate the initial sum of the first k cards and then adjust the pointers to include cards from the end while excluding cards from the start. This method is conceptually similar to sliding window and offers comparable efficiency, making it easier to grasp for some candidates. Lastly, there's the dynamic programming approach, which involves building a DP table to store the maximum points for specific ranges of indices. While this method is more complex to implement and has a higher time and space complexity at O(k²), it can be a useful alternative in certain scenarios. Each of these approaches has its own strengths and trade-offs, so understanding them will allow you to choose the most appropriate solution based on the problem constraints and requirements. Great job on completing this problem. To wrap up, we summarize the key insights gained, including the importance of strategy and optimization. Remember to practice similar problems to reinforce your skills. Thank you for watching, and I hope to see you tackle more challenges with confidence. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!